So hi everyone. Like you said, my name is Khadijah, and today I want to be talking about a project that I guess I'm working on slash basically done. The title of the paper is Enhancing Fairness and Performance in Prediction Models. It's a multitask learning approach that involves Monte Carlo Dropout and pareto-optimality. So I'm just gonna go right into it. First, I just want to go through some background on bias and fairness in machine learning, and just like some general definitions in the field. So fairness, as defined by this author, is the absence of any prejudice or favoritism toward an individual or group based on their inherent or acquired characteristic. So basically, an unfair algorithm is one whose decisions are skewed toward a particular group of people. And there are several ways that bias could be introduced into a machine learning pipeline, and they're usually grouped into these three major categories. So through data collection, at the data labeling stage, or during model training. So at the data collection stage, if certain demographic categories are missing from the data, these models developed on this data can fail to generalize when applied to new data that contains those missing categories. So that obviously introduces bias into the prediction. And then during the data labeling stage, we know that the majority of models deployed in, machine learning algorithms are based on, they're supervised machine learning models. And most of the labeled data comes from people. And as people, are inherently biased, this bias could easily be transferred through this labeling stage. And then lastly, through model training, when we have, even if we have a large, appropriately sampled data set and labels that have a minimal degree of bias, there's still the risk of introducing bias from the features and modeling techniques that are used in that model. We know that machine learning obviously is at the forefront of a lot of industries now, and it is, it's really led to some development where, it is time saving and it provides insights that might otherwise we would not be able to exploit. Even with that, there is a lot of cases of bias that have been introduced in machine learning algorithms throughout the years. And just the popular ones, one of them is the correctional offender management profiling for alternative sanctions, which was, I think it was about, I'm missing it. I think it's about repeat offenders in the justice system, and it was actually deployed and used a bit in the US before it was discovered to be biased against Black people. And then Amazon's recruiting engine, which they used for a short while, was biased against women. And if we switch gears to health, there are certain models that have been shown to be biased. For example, the prediction of future administrations of benzodiazepines. And these are prescription drugs that are used in the treatment of, for example, anxiety or insomnia. And these were shown to be biased against women as well, these models that were built. And this is dangerous because the long-term use of a drug like this is actually associated with increased medical risks such as cancer. They're also in high doses, they're addictive with complicated withdrawal symptoms. So there's also models that were built for the prediction of postpartum depression, and those were shown to be biased against Black women. So we can see that, there's a lot of examples of how bias in machine learning could be really harmful when deployed without, proper assessment. So this kind of leads me into the motivation of this work. So basically, in recent years, research on bias and fairness in machine learning has shown that simply eliminating the sensitive feature from the models working is not sufficient to avoid biased outcomes. And this is caused by the sort of indirect influence of the sensitive information on other features that are vital to the algorithm's decision-making process. One study actually mentions that the use of high-dimensional or black box prediction techniques that are typically favored in machine learning community right now is generally problematic, since these approaches can predict the protected label through other variables, whether or not the actual protected label is explicitly encoded in the model. So given these scenarios, it is understood that reducing model bias may not necessarily be sufficient in eliminating fairness concerns in decision contexts that are associated with certain fields, fields such as healthcare, like we mentioned, because these could be quite complex with the amount of data and the dimensionality of data that we use, and unintuitive and often hard to explain. And then another setback with developing methods to mitigate bias is the trade-off between performance and fairness, which is very present in existing literature. And as a solution to this issue, actually I didn't mention them here, but several previous works have used the concept of pareto-optimality from multi-objective optimization to kind of seek a fairness accuracy Pareto front for a classifier, which I'll go more into because it's also part of the method that I am. What do you say? What's the word? Introducing. Yeah. Yes. And then obviously, additionally, like machine learning plays a more significant role in decision making across industries. The demand for domain agnostic and easily transferable bias mitigation methods is increasing. And a lot of these mitigation methods are unique and proprietary. And a lot of machine learning algorithms already face very specific challenges relating to bias. And the current solutions that target specific problems are not really broadly applicable to different industries when it comes to bias mitigation. So there's sort of like a need for that as well. So just going into that, what we do here is propose a bias mitigation method that leverages model uncertainty to enhance model fairness. And it does this also by integrating multi-objective learning for an optimal balance between fairness and performance. So that leads us into the contributions of this work. So in this work, we propose a multitask learning-based bias mitigation method that utilizes Monte Carlo Dropout for uncertainty estimation. This operates independently of the model's objective function and prediction method. So in this way, we avoid using the sensitive data in the model's functional form. And then we also integrate multi-objective learning through pareto-optimality to balance fairness and performance. And then we validate this proposed method on 3 classification-based data sets. I don't know if any one of you is familiar with fairness, but adult is a very commonly used data set in the fairness field. Almost all the papers use it. And then there's MIMIC3, which is a very popular data set in health as well. And then we use one non-public data set as well, which is called Snapshot. So adult is sort of like finance because it predicts salary. MIMIC is a health data set. And Snapshot is more of like a behavioral mental health kind of data set. And then we propose, we compare this proposed method with reweighting, which is a standard pre-processing bias mitigation method. And then two other methods that were introduced in previous works, one is called adversarial reweighted learning, and then there's FAIR RF, which I will not really get into too much because I have a lot to present, but I'll touch up on later. And then lastly, we also visualize the effectiveness of the proposed method and significance of the model weights through feature importance. And we did this to kind of improve our understanding of how input features influence final predictions. And the visualizations we have also highlight the impact of our proposed method on the network's prioritization of features for prediction. So just some more background information. So I'm just gonna touch up on like a little fairness terminology. I don't know how, comfortable people are here with it, but just like a few of the terms that I'll be using for the rest of the presentation. So the first one is the protected label, and this is just the attribute that partitions the population into groups, whose outcomes we're trying to make them have parity. So for example, race or gender, income, nationality, whatever you want to choose. And then, so there's the privileged class and the unprivileged class. So the privileged class is usually the class that is historically or socially been proven to be more, there's prejudice against the other class. So for example, it depends. Women, men, when you have, societally and stuff like that. So these are the two classes. And then for the fairness metrics that we're going to use in this paper, in general, there's a lot of fairness metrics and definitions of fairness, but specifically in this paper, we're going to use the disparate impact ratio, which is the measure of how different outcomes are for different groups based on the results of a model. And it is represented by the ratio of positive outcomes in the unprivileged class divided by the ratio of positive outcomes in the privileged class, shown in like this equation here. And we used an acceptable bound. So the ideal score for this would be 1. But the acceptable bounds that we use in this work is 0.8 to 1.2 based on previous works. And then the other one is equalized odds, which basically it sorts to create the same proportion of true positives and false positive rates. So basically it tries to have the model correctly identify the positive outcomes at equal rates across groups, and also misclassifies positive outcomes at equal rates across groups. So now I'm gonna be going into the proposed method. It's gonna be a bit long, so just bear with me. Not long, but it's like a bit confusing, so just bear with me. I'm gonna talk slowly. So basically, our proposed method is based on the premise of Bayesian uncertainty estimation to address fairness in machine learning models. So in this case, uncertainty estimation is just simply estimating the confidence level of a model output. So in our proposed method, what we hypothesize is that when a model exhibits the greatest range of uncertainty regarding the protected label, it indicates a deficiency in knowledge within specific areas of the feature space linked to that label, right? And this approach is based on our findings that a spectrum of model weights rather than a single optimal model yields the best fairness scores. This finding, I did not cite it, but it was from our previous work that we did. So this work is sort of an extension of that other work. And so what we do is that we utilize the model weights from this range of uncertainty for predicting a target label. And then so it's likely to diminish the influence of the protected label on the final prediction outcome. And this is based on the premise of epistemic uncertainty, which is basically uncertainty in the structure and parameters of a model that is caused by a lack of knowledge. So last, we use non-dominated sorting to identify the Pareto-optimal set of solutions. And this method kind of allows us to select models that effectively balance fairness and performance by recognizing the improvements in one metric. Meaning like improvement in one metric may lead to reductions in the other. So this provides sort of a more robust framework for addressing fairness. So to accurately assess the uncertainty associated with both the target and protected labels, we first implement a multitask learning framework. So this here, and this optimizes the learning of correlated tasks by sharing common features while allowing for task-specific adaptations. So this framework uses a shared input layer, but distinct output layers for each task, right? And then one is for the primary target prediction and one is for the protected label. So basically, this framework is rooted in the principle that related tasks can share useful information, and so it can learn more effectively together than separately. And based on our assumptions, our hypothesis, this model structure kind of looks something like this. So what we do is we first predict one protected label, for example, gender, and the target label at the same time using a multitask learning model. And then we save the model periodically in our experiments and implement Monte Carlo Dropout, which allows us to get uncertainty estimations of these saved models. So going into Monte Carlo Dropout, which is what we use for uncertainty estimation, the way it works is that it runs multiple forward passes through the model with a different dropout mask every time. So each time the model's architecture is slightly different. So it draws weights from approximate posterior distributions. The posterior distribution is just a way to sort of summarize what we know about uncertain quantities in Bayesian analysis, and it combines the prior distribution and the likelihood function, which tells us information in the observed data, basically the new evidence. Yes, I said that. And then so in the end, this algorithm just iterates through different combinations of dropouts, and then it produces a distribution of predictions, and the accuracy and uncertainty scores can then be calculated among other things. Okay, so just a quick, I guess, diving into the way Monte Carlo Dropout works mathematically. This is something that's, I mean, are you guys familiar with it? Monte Carlo Dropout. No. Yeah, okay. Do I need to go over this or should I just go on? Because there's a lot of slides that I have, so I'm asking. Okay, I'm just gonna go slightly over it. So basically, let's say we're given a trained neural network with dropout F, and X represents a single sample. So the result of Monte Carlo Dropout will look something like this. It collects the predictions of T inferences with different dropout masks. So here, this represents the model with dropout mask BI. So a sample of the possible model outputs for sample X is obtained as this. And then by computing the average and variance of the sample, we obtain an ensemble prediction, which is the mean of the model's posterior distribution for the sample, and then an estimate of the uncertainty of the model when it comes to X. Okay, so going back to our figure, which is more complete now, from the saved model that we from the saved models that we obtain using Monte Carlo Dropout, we compute the uncertainty scores and extract the parameters for each model. And then these parameters we then use in distinct non-multitask models that are dedicated to predicting the main target label, which is our actual prediction model. We train these models, we monitor their performance metrics and compute the fairness metrics as well, including the disparate impact ratio or the differences in false positive or negative rates from their predictions. And then next, to identify the most effective models in terms of balancing performance and fairness, we apply a non-dominated sorting algorithm to the ensemble's performance and fairness scores. And we particularly focus on the disparate impact ratio score because it's one score and it's pretty easy to understand, I guess. And so basically this process allows us to derive the Pareto optimal set of models that are, sorry. So these models are collectively known as the Pareto front or Pareto frontier. So basically models on this front represent the optimal trade-offs between performance and fairness, and any improvements in one metric would necessitate sort of like a compromise in the other. So one is not better than the other technically. So this front is obviously significant since it contains no models that outperform the others across both methods simultaneously, which kind of shows us the inherent trade-offs that I was talking about between achieving high performance and maintaining fairness in the field. So this is the algorithm that we use, the non-dominated sorting algorithm that we use. So the way it operates is by comparing models based on their performance scores and fairness scores. And for us, this is specifically the disparate impact ratio scores. So the algorithm's objective is just to maximize the performance scores while minimizing the absolute difference between the fairness scores and the ideal value of one. So what it does is that it identifies the Pareto optimal points from two metric arrays, which is the X's and Y's, which represent the conflicting objectives which are the fairness and performance. And then the algorithm pairs these metrics and sorts them based on the X's value according to the preference for maximization and minimization. And then it iteratively constructs a Pareto frontier. So each pair of X and Y that comes after is evaluated against the last point on the frontier, and then it is then added if it offers an improvement in Y without worsening X. And then what it returns is two arrays, so the P front X and P front Y, which show the optimal trade-off between the evaluated metrics. And then moving on to the data sets. Adults, like I said, publicly available. It has in total 14 categorical and continuous integer variables. But there's a lot of noisy data, and so people usually clean it up, and it ends up being like 8 features after. Then we have Mimic3, which is also publicly available de-identified health-related data from over 40,000 patients who stayed in a critical care unit. And then Snapshot contains multimodal physiological behavioral and survey data from 350 college students in one university, and it totals over 7,500 days of data. So in total, it has 378 features. And just going more into features. Adults, these are just the breakdowns of the features in each of the data sets. Obviously, Snapshot, I didn't write all the features because there's like 378 of them. But and also Mimic as well, that's not the complete set, but just gives you an idea of the features. And then the target variables are salary in hospital mortality, and then this predicts mood. So moods in the morning and evening, so happiness and calmness, morning and evening. They're all binary labels. And then for the protected labels, what we chose to be the protected labels in our experiments, adults, we chose age, race, and sex, or gender, which, again, from previous works, that's generally what's been used. And these are how we categorize them into the privileged class and the unprivileged class. And Mimic, we used age, gender, insurance, because there's research that shows that people who are under Medicare and Medicaid, which are government-sponsored insurance types, are usually shown to be less well-to-do, right? So they're more prone to, yeah. And then we use marital status as well, because there's research behind having a partner in your life to take care of you greatly and affects health. And then for snapshot, we use gender, race, ethnicity, and then these last 5 features are personality-based features. And this was purely experimental. We just thought, this might be interesting. So we chose to also test on these. So the structure of the way our experiments are set up, we first build a baseline model, prediction models, and then we do fairness analysis on them. And this is important to mention because a lot of works that I've seen in fairness research, sometimes they just go straight into bias mitigation. They don't check if the bias is actually present. And that's something I always mention. So first, we do a fairness analysis to see if there's actually bias present in the model. And then we implement our proposed method and then compare with the 3 baseline models. So reweighting simply just works by what it does is that it applies appropriate weights to different tuples in the training data set to make it discrimination-free with respect to the protected label. ARL uses an adversarial setup to reweight the features for fairness, which presents sort of like a direct method to manipulate feature importance based on the impact on bias. And in contrast, our proposed method, which uses the Monte Carlo Dropout, offers a more probabilistic view of feature importance by assessing uncertainty. And then FAIR-RF focuses on mitigating bias through direct feature manipulation. And this also provides a direct contrast to our methods used of uncertainty estimation to influence model predictions. And with this comparison, what we're trying to do is sort of to illustrate how managing uncertainty can potentially be more effective than directly modifying feature weights. And then lastly, the visualization of feature importance. Okay, so the baseline model for adults is a prediction model for salary, which is binary. It predicts whether a person earns less than or equal to $50K or greater than 50K. It's a CNN model. We use 3-fold cross-validation, binary cross-entropy, protected labels I've mentioned now, and this is just kind of the breakdown of the model. And after running the model and analyzing for fairness, this figure shows the disparate impact scores for each of the 3 protected labels. And obviously 1 is the ideal score, and then our range of acceptable scores is 0.8 somewhere here, and to 1.2 to 0.8. And as we can see, all of the model is outside of those bounds for all 3 protected labels. So that means it is biased by all of these 3 labels. And then what we do to implement a proposed method is we predict salary plus each of these protected labels separately with a loss weight ratio of 4.5 to 0.25. And this loss weight ratio was achieved through this experimentation to see what works the best in terms of performance of the model. And we trained this 400 epochs, so it gave us an ensemble. We saved at each epoch, gave us an ensemble of 100 models. And then we calculate the uncertainties for each of these saved rate combinations and use the parameters to then predict salary. And then we apply the non-dominator sorting algorithm and plot, and then we choose the models that we want to choose. Okay, so these are the plots for the Pareto fronts for the models for each of the protected labels. And the models circled in green are the models we chose. So the x-axis is 1 minus the disparate impact ratio. So obviously you want the difference to 1 to be less. So the lower, the better. And then obviously performance would be the higher, the better. But there's not much difference in terms of performance between all of the models. So we focused on choosing the most fair models in these scenarios. Yeah, except this one. Why is it not moving? Oh. Okay. And then, yeah, so after choosing those models, we compared them with the baselines. And as we can see, so our model for our proposed methods are those in green over here. So the x-axis shows the difference in accuracy from the baseline. So you want it to be higher, right? So we don't want it to be in the negative, so we want it to be positive. And then x-axis, y-axis. The x-axis is 1 minus the disparate impact ratio, and also we want the ideal to be less. And as we can see, so the baseline is purple. This one is far off here. In general, our model performs pretty well when you look at the average between all three protected labels. The most similar performing method is the ARL. But if you look at each of the protected labels, ours is still better performing in terms of fairness, right? But again, it's very close. In terms of reweighting, they do well in preserving performance, so preserving accuracy, but then you have the model for age, which is a lot far off on the side. So in terms of fairness, it doesn't perform as well. Actually, it seems like for reweighting for fair RF and the baseline model, the models for age are the worst performing in terms of fairness. And then just to kind of visualize the feature importance and how things shift after a proposed method is implemented, we obtain kind of these figures. So the figure on this A figure shows the feature importance for the demographic labels themselves. If you were to predict them, these are the most important features for those predictions. And then the figure in B shows the feature importance for the models for the target label, but after implementing, so this one is the base, and then this one is after implementing our method based on age, based on race, and based on sex. So just in general, we can see that the work class feature holds the most weight across the board, right, for all the features, and it remains equal even after the proposed method implementation. And then we have the relationship feature, which holds no weight in any of the prediction tasks across all experiments, so it's not really on this figure. So the changes in the importance are demonstrated more on the three remaining features, which is education, marital status, occupation. And as we can see, for example, for age, this age is highly dependent on work class, but not very dependent on the other three. But after implementing our method, the dependency is sort of more equal and shared across the board, so it's not depending on one feature as much. And we can see that trend for race and for sex as well. And so, yeah, this is just kind of to show more explainability. And then for the baseline model for MIMIC, it predicts in-hospital mortality, which is binary. It is an LSTM-based model. This model we did not build ourselves. It's just something we reproduced, experiments we reproduced from an earlier work, which is highly used in literature. Again, the protected labels are age, marital status, gender, insurance, performance metrics, accuracy, AUROC. And then initial fairness analysis shows that it was biased by marital status alone and not the other three. And so we only implemented our method based on marital status. So again, same scenario like with adults. I'm not gonna spend too long. Loss rate ratio is 5 to 0.5. And then we did the same thing where we calculate uncertainties of each saved weight, use parameters in predicting exit salary, supposed to be in hospital mortality. And then we apply the algorithm and plot and choose the models that are best performing. We chose, again, another reason, actually, I don't know if I mentioned this, but another, I guess, thought process for implementing this non-dominated sorting is to give sort of proprietors of, people that might use machine learning models or this method for bias mitigation, sort of more of a freedom to choose what their preferred outcome would be, right? And so this is like a good example. The two really good options are this model 40 or model 23. And looking at the numbers, the model 40 performed best in terms of performance and fairness. Compared to reweighting, the performance is pretty similar, but the fairness is better, higher. So this was the baseline model, disparate impact ratio, and after the implementation, it becomes 1.043. And then for a snapshot, we predict 4 binary labels. Is a GRU-based model, and the performance metric was F1 score, and we experimented on 8 protected labels, like I mentioned earlier. So this kind of just shows the F1 score for the baseline model was approximately 0.7 or 0.8 for all the target labels, all 4 of them. And the disparate impact ratio, this shows the disparate impact ratios for the baseline model, and then we tested the initial trained data and the initial test data as well. And most of them are within the acceptable range, except one, which is for evening, sad, happy label when evaluated by race. Again, we did the same kind of procedure for this as well, and obtained this where our chosen model is 53, and it improved, it actually improved the fairness by 0.1, and then with reweighting, compared to reweighting, it did give us a perfect disparate impact ratio, but the performance dropped by 37% from the baseline. I'm not going to spend too much time here because it's very confusing, but these are saliency maps for the snapshot model, right? And the one on the left, the side is the baseline, and this is after the proposed method is implemented. So the deeper red shows features that hold more weight, and then therefore they're more important in the target prediction. And these are across the 7 time steps because we use time step of 7. From these figures, we can see, so there's actually 1, 2, 3, because again, 378 features. So I had to break them down. But we can see that a few features, hold the most importance, right? And after implementing the method, it's more spread across. And you can see the importance actually taken away from some of these features. So this shows sort of how, I guess, hypothesis is correct. Or, yeah. So yeah, that's all I wanted to show with these features. Sorry, with these figures. So I'm just gonna move on to, another thing we did with snapshot, because we did a lot of experiments with 4 labels and 8 protected features, and only one of them was biased. So we decided to do data manipulation to see if that would affect the fairness. So we kind of removed some samples from a specific demographic label from the female participants. And then we again analyzed, and then we found that one model was now biased by gender. And we ran our experiments same way and found, the appropriate models that improved the fairness scores with a 6.5 drop in performance from the baseline. So in conclusion, for the adults data set, just to round up some of our results, we found that it was biased by age, sex, and race, and we improved with our proposed method. We're able to improve the disparate impact ratio scores to within the ideal threshold of 0.2 and 0.8 and 1.2. And our method definitely performed better than reweighting in terms of fairness and the other baseline methods that we compared it to. The closest, I guess, in terms of fairness was the ARL method. Then in average, there was a decrease of 1.7% accuracy for all 3 protected labels. And we also showed that our method shifted importance from features that highly correlate with a particular protected label, and that then reduces its effect on the final target label prediction. For mimic, we found that the baseline was only biased by marital status. We were able to improve the disparate impact ratio score to 1.04. And then this also improved performance of the baseline. It improved performance by accuracy by 1.7 and 19.4, 18.6. And compared to reweighting, which improved both fairness and prediction performance is better. This actually was stated in a previous work where they said that ensuring fairness does not always lead to a drop in utility, and sometimes it might even lead to enhanced performances under certain circumstances. And then for snapshot, it was only one model was biased by race, and we were able to improve the disparate impact ratio score, and it did not have a significant effect on fairness. Reweighting gave us a perfect disparate impact ratio score, but the performance highly diminished by about 37%. And then we did data manipulation, which kind of gave us the same trend of results that we had. And again, saliency maps showed the same trends that the ones for the adults showed as well. So in terms of performance fairness trade-off, we were able to show that enhanced we were able to enhance performance fairness straight up using the concept of pareto-optimality. And then we were able to obtain a set of pareto-optimal solutions that gave us the most ideal models to choose from, whether fairness or performance, whatever you prioritize according to application or type of data. And we utilize this feature of our method to obtain models with the highest fairness score, since the variability in performance scores was generally low across our experiments. So this provides flexibility for the proprietor to make a choice of what objective to prioritize. And in addition, by demonstrating which features, most influence model predictions and adjusting feature weights away from the protected label, our approach actually promotes transparency and mitigates disparate impact of unprivileged groups. Some of the limitations that I would say of this work is obviously the restriction to binary outcomes that are imposed by the tools that we use and the labels as well. We use the IBM AIF 360 library for the fairness analysis. And then there's also still, I think, a general lack of agreed upon definition of fairness in the field. And this is because in the area of machine learning, most of the attempts that come at proposing new fairness constraints or fairness metrics for algorithms have come from the West. And most of the works use the same data sets and the same problems to show how their constraints performs, which means that there's still no sort of explicit agreement on which constraints are most appropriate for what problem. So it'd be interesting to see if there's like an in-depth review of what these fairness metrics and constraints mean for different applications. And so, yeah, and then also computational complexity, obviously, for using Monte Carlo Dropout, saving, loading models and all that. But yeah, so that's it. The end of my presentation.